Through types of forces today. So first we probably need to define forces. A force is just a push or pull, and that push or pull will act on one object, and it can be balanced. They can be balanced or they can be unbalanced. So if you think about Newton's first law, objects at rest stay at rest, objects in motion stay in the same or constant motion, unless unbalanced forces are acting. So as long as forces are balanced, then objects don't change what they're doing. But when forces become unbalanced, then we see changes. And so in physics, we call changes acceleration. Okay? In your notes, you might add a little note that this has to be unbalanced in order to cause an acceleration. And that could be a speed up, could be a slow down, could be a change in direction. Okay. One quick clarification is there are always forces that are acting on objects. So even objects at rest have forces acting. They just happen to be balanced. Okay. Okay, so in general, we've got field forces that do not require contact. And we have contact forces, which, as the name would imply, do require contact. And we're going to look at both of those. We'll start with field forces. So a force field is not just for sci-fi movies. They are real. And there are three main ones that we'll talk about, and one of those that we'll focus on in this unit. So with a field force, we call it action at a distance. In other words, the force makes an effect, but the two objects never have to touch each other for that to happen. Okay, so if you've ever jumped off of something, then you've experienced a field force of gravity, and you know that it doesn't matter if you're in the air, it doesn't matter if you're on the ground, on a roller coaster, in a tree, wherever you are and whatever you're touching, gravity is acting. Okay, so gravity is just a pull towards the center of the earth, the force of gravity that we're focused on in this unit. And it does not matter what you are touching, so we call this a field force. Gravity will act on you wherever you are, okay? A second one you might have played with maybe in elementary school is if you played with magnets and you discovered that you could repel or attract them without the two magnets ever touching. Like if you had one under your desk and you could move the one on the top of your desk. That is a magnetic force, and magnets also do not have to be in contact to apply forces to each other. Okay, and then the first one on our list is called electrical forces. So if you think about it, electrons are in those negative energy clouds around the outsides of an atom. Positive protons are on the inside in the nucleus. And it's kind of crazy that atoms stay together because all those protons should be repelling each other. All the electrons are repelling each other, but the protons and electrons are attracting each other. So there's quite a bit going on in an atom. There are very strong forces called electrical forces that keep the atom together. They keep those protons from flying apart. And there's a super important, think about it, if atoms don't stay together, then we don't have any more universe, right? If we don't have atoms, we have nothing. So electrical forces are field forces because the protons and electrons never have to come in contact to feel the force. Magnetic forces are field forces, and gravitational forces are field forces. Okay, we're going to look at these forces in electrical and magnetic when we get to the end of the class, like December-ish, end of the semester. We'll come back to those. For now, we're just going to focus on gravity. Okay, so we're specifically talking about the force of gravity, and we talked yesterday about how we symbolize that with a capital F and a little subscript G. We also know that force of gravity is the same thing as weight, right? When we are thinking about forces, direction is important. Forces are vectors, okay? And so we have specific ways that we want to draw the force vectors. So for gravity in particular, it is always straight down, no matter what the object is doing. So with force vectors, you're going to start them in the center of the object to kind of represent the center of the mass. Okay, and if you've got a box sitting on a flat surface, gravity is pulling down towards the center of the earth. If you have a box on a hill, gravity is still pulling straight down towards the center of the earth. So it doesn't matter whether it's inclined or whether it's flat, we still have a straight down gravity. Um, Also, we have straight down gravity even when it's something flying through the air, and it could be flying up, could be flying down, could be going to the side. No matter what direction the object is moving, gravity is pulling down towards the center of the earth. Okay, so those are force vectors for gravity. And that brings us to contact forces. So, contact forces are exactly what they sound like. They occur when things touch, when there's contact between one object and another. And we'll look at several. They're often called everyday forces because we encounter them often. Okay, so this first one is called a tension force. We're going to symbolize it with this little capital F and subscript T. And this just has to be applied by something attached to the object that can provide tension. So, for example, if you like to take your dog on a walk, or maybe your dog likes to take you on a walk, whoever's pulling on that leash is experiencing tension, right? The tension is along the leash in the direction of the pull. Okay, so when we're drawing our vectors, we draw it along whatever's causing the pull, and we also draw in the direction of the pull. So if I have this box hanging from the ceiling, the tension is going up, right, along that rope. Even if the box is not moving up, the tension has to balance the downward force of gravity, and so tension is pulling up even if the box is at rest. Okay, if you've got more than one rope, then you've got tension forces along both, and so you just would draw them both in, and again, they're along whatever's causing the tension, the rope, string, leash, whatever it is, and they are pointed in the direction of the pull. The next one we want to look at is called the normal force. So F with a little sub N. The normal force is caused by surfaces, and that can be any kind of a surface. So the surface of the chair you're sitting in right now, the seat, is a surface providing a normal force. Your floor is a normal force keeping you from falling, especially if you're on the second floor. You're not falling into the first because of that normal force from the floor. If I put my phone on my hand is a normal force. Okay, so anything that's a surface could be a normal force. And the normal force is always pushing perpendicular to that surface. So the name actually comes from a math term. If you think about the symbol for perpendicular in math, it kind of looks like this little upside down T. And this line right here is the normal line, is perpendicular to the horizontal. Okay? So when you draw a normal force, it needs to be perpendicular to the surface. So in our first example, we have a box sitting on a flat surface, and so perpendicular to that would be our normal force, and it's pointed up. If you have a box on an incline, remember you have to be perpendicular to the surface. So here's our surface, right? So our normal force is going to be at an angle perpendicular to that. Okay. Something very cool about the normal force is that it's a compensating force. So imagine that you are putting some weight on the floor. Weight is going down. Now maybe you decide to jump. Okay, so you jump and you put more force down on the floor. Well, assuming you don't fall through, the normal force has just grown. It's gotten bigger to compensate for that extra force you're putting on it. Another example would be like if you take your hand and press on the table wherever you're sitting, you feel the table push back, right? It's pushing up, perpendicular to your hand. Now push harder. What does the table do? It pushes back harder. Okay, so the normal force is something that can grow based on what it needs to support. All right, our last two forces are applied force and friction force. So let's start with applied force. It has to be applied by some object, as the name would imply. The object has to be touching, okay? So for our example, let's say we've got a little person here who's going to push this box. Let's say the push is to the right. We would draw our applied force in the direction of motion. Notice again that I've started it in the center of the object and I didn't draw it right here, okay? We want to draw it from the center of the object. When you get to net force, you'll kind of see why that is. But for now, just know it always starts at the center, always points away from the object. The applied force is going to be in the direction of motion always. Now, a really common misconception is that if an object's moving, it has to have an applied force. but that's actually not true. Imagine that you're in our main hall and I decide that I'm going to push you in a rolly chair. As long as my hands are actually on the chair and I'm pushing you, then there's an applied force. If I let go, there's no more applied force, but your chair's not going to stop, right? You're on slick tile, you're going to keep on moving. You just don't have the ability to change anything anymore, okay? But objects can be in motion and not have an applied force, so be careful about that. Always look for there to be an object that's actually making contact, as applying the force, okay? All right, and then our last one is friction. Friction is considered an opposing force, so it's opposite of motion. We'll talk in depth about friction in a couple of days. It's a super important force. We wouldn't be able to move without it. However, we always draw it in the opposite direction of the motion because it is opposing the motion. So imagine our guy is pushing the box on carpet. There's a good amount of friction that's going to be opposite the applied force, okay? We do have actually several types of friction. If you've ever been in a swimming pool, you've felt fluid friction, right? You feel the resistance from the water. We are going to bring air resistance back into our problems. Y'all are ready for that now. So air is coming back in. And then any two objects sliding together, whether that be your hands generating heat or a box on the floor, both of those are sliding friction, okay? All of that is symbolized with this F, little sub F, no matter what type. So air resistance and carpet friction are both capital F with a little sub F, okay? So those are your types of forces. When you put all that together, then you can take a look at net force.